Good morning, children. How are you? Are you safe and fine? Okay. Now we will see the second lesson in a second volume, that is electrochemistry. In this lesson, already we studied about the galvanic cell, then Daniel cell, EMF, and the other things we studied. Now we are going to see the batteries, about the batteries. Okay. There are two types of batteries are there. That is nothing but primary batteries and secondary batteries. Okay. Primary batteries are the batteries which cannot be reused. Okay. Secondary batteries we can reuse. Now you take the lesson electrochemistry batteries. Okay. Shall we start? Okay. Batteries are indispensable in the modern electronic world. For example, lithium-ion batteries are used in cell phones, dry cell, in flashlight, etc. These batteries are used as a source of direct current at a constant voltage, and we can classify them into primary batteries, that is non-rechargeable, and secondary batteries, those are rechargeable. In this section, we will briefly discuss the electrochemistry of a few batteries. First is Leclanche cell. Here the anode is zinc container. The container itself is act as a anode. Then cathode is a graphite rod which is in contact with MnO2. That is nothing but manganese dioxide. The electrolyte, that is the solution that we are taking, is ammonium chloride and zinc chloride in water. The EMF of the cell is about 1.5 voltage. The cell reaction, oxidation, we know oxidation takes place at anode. So zinc is the anode. Zinc is a last electron and it converted into zinc 2 plus. So the equation is zinc solid gives zinc 2 plus plus 2 electrons. And reduction takes place at cathode. That is NH4 plus. In aqueous solution, it accepts those 2 electrons and it is converted to NH3 and H2 gas. The hydrogen gas is oxidized to water by MnO2. H2 and MnO2 gives Mn2O3 solid and H2O liquid. And if you are adding the first equation, second equation and the third equation, you will get the overall equation as zinc solid plus ammonia plus 2 MnO2 gives zinc 2 plus in aqueous, Mn2O3 as solid, H2O as liquid and ammonia to NH3. Here the ammonia produced at the cathode combines with zinc 2 plus to form a complex ion, that is zinc NH3 4 times 2 plus. As the reaction proceeds, the concentration of ammonium will increase and the aqueous ammonia, NH4 is nothing but the ammonium ion, NH3 is the ammonia, will increase with which led to decrease the EMF of the cell. Next is mercury button cell. In this one, the anode is zinc amalgamated with the mercury and cathode is HgO, that is mercury oxide used with the graphite, and the electrolyte is a paste of KOH and ZnO. Okay, that is zinc oxide. Oxidation occurs at anode, that is zinc 2 plus 2 OH minus in aqueous gives zinc oxide plus water plus 2 electrons. Reduction takes place at cathode, that is HgO plus H2O liquid plus 2 electrons gives Hg plus 2 OH minus in aqueous solution. So the overall reaction is Zn solid and HgO gives ZnO and Hg in liquid. The cell EMF is about 1.35 voltage. Uses, it has a higher capacity and longer life, used in pacemakers, electronic watches and cameras. And the device is given here. The first, this picture shows the button cell, and here the part is given. Okay, that is the inner side. You have the first, you have the seal outer top, then outer steel case, And then inside you have the sealing of the insulated gasket. Zinc as an anode and KOH is saturated with ZnO. Adsorbent is act as an electrolyte and cathode is at the bottom of it, that is HgO mixed with the graphite. Next we are going to see the secondary batteries. As I have already told you, we have the electrochemical reaction which takes place in a galvanic cell may be reversed by applying a potential slightly greater than the EMF generated by the cell. And this principle is used in the secondary cells to regenerate the original reactant. That is, these batteries are reusable, rechargeable. Let us understand the function of secondary cell by considering the lead storage battery as an example. Lead storage battery. In this one, the anode is spongy lead. The cathode is lead plate bearing with lead oxide, that is PbO2. The electrolyte is 38% by mass of sulfuric acid with the density 1.2 gram per milliliter. Oxidation occurs at anode. Pb is converted to Pb2 plus and it emits or lost 2 electrons. This Pb2 plus ion combines with SO4 minus to form PbSO4 as a precipitate, that is lead sulfate as a precipitate. Pb2 plus and sulfate ion gives lead sulfate. Reduction occurs at the cathode, that is PbO2 plus 4H plus ion in aqueous. It accepts those 2 electrons and it is converted to Pb2 plus and 2H2O liquid. Here Pb2 minus ion combines with SO4 ions from the sulfuric acid to form lead sulfate precipitate. Pb2 plus aqueous sulfate gives PbSO4. The overall reaction is equation 1 plus 2 plus 3 plus 4. If you are adding all the 4 reactions, you will get lead plus lead oxide plus 4Hi plus 2 sulfate ion gives lead sulfate and water. The EMF of the single cell is about 2 voltage. Usually 6 cells are combined in series to produce 12 volts. The EMF of the cell depends on the concentration of sulfuric acid. As the cell reaction uses sulfate ion, the concentration of sulfuric acid decreases. When the cell potential falls to about 1.8 volt, the cell has to be recharged. And these secondary cells are rechargeable cells. Next, recharge of the cell. As we said earlier, a potential greater than 2 voltage is applied across the electrodes. The cell reaction that takes place during the discharge process are reversed. During the recharge process, the role of anode and the cathode are reversed and H2SO4 is regenerated. That means anode is behaves as a cathode and cathode behaves as an anode for the reversible reaction. So oxidation occurs at the cathode. Now it is acts as an anode. So PbSO4 plus water gives PbO2 plus 4H plus SO4 2 minus with the 2 electrons liberation. Reduction occurs at the anode and now this anode is act as a cathode. PbSO4 plus 2 electron gives PbS and SO4 2 minus aqueous solution. So the overall reaction is PbSO4 solid plus 2H2O liquid gives PbS solid and PbO2 solid and 4H plus ion in aqueous and 2SO4 2 minus ion in aqueous. Thus the overall cell reaction is exactly the reverse of the redox reaction which takes place while discharging. Uses, and these are all used in the automobiles, trains and inverters. The next is lithium ion battery. Anode. Here the anode is the porous graphite and cathode is the transition metal oxide such as cobalt oxide. And the electrolyte is lithium salt in an organic solvent. At the anode, oxidation occurs. Lithium gives lithium plus 1 electron and at the cathode, reduction occurs. So lithium accepts that 1 electron along with the cobalt oxide and it gives lithium LiCO2, lithium cobalt oxide. So the overall reaction is lithium plus cobalt oxide gives lithium cobalt oxide, LiS. S is nothing but the solid state and cobalt oxide COO2 gives LiCOO2. Both electrodes allows lithium ion to move in and out of their structures. During discharge, the lithium ions produced at the anode and moves towards cathode through a non-aqueous electrolyte. When a potential greater than the EMF produced by the cell is applied across the electrode, the cell reaction is reversed. That is, the reversible reaction will take place. And now lithium ion moves from the cathode to anode, where they become embedded on the porous graphite electrode. And this is known as intercalation. Uses. And this is used in the cellular phones, laptops, computers, digital cameras. Next is fuel cells. The galvanic cell in which the energy of combustion of fuels is directly converted into electrical energy. It is called the fuel cell. So wherever the energy, the combustion of the fuel is converted into electrical energy, means such a type of cells are called fuel cells. It requires a continuous supply of reactant to keep functioning. The general representation of the fuel cell is fuel slash or a vertical, single vertical line, electrode, single vertical line, electrolyte, again single vertical line, electrode, and then oxidant. Now let us understand the function of a fuel cell by combining hydrogen oxygen fuel cell. This is one of the important question. Okay. In this case, hydrogen acts as a fuel and oxygen acts as a oxidant, and the electrolyte in aqueous KOH maintained at 200 degrees centigrade and the pressure is 20 to 40 atmospheric pressure. Porous graphite electrode containing nickel and nickel oxide serves as an inert electrodes. Hydrogen oxygen gases are bubbled through the anode and cathode respectively. As usual, oxidation occurs at anode. So H2O plus OH minus is converted to H2O and along with the liberation of 4 electrons. Reduction occurs at the cathode, that is oxygen plus water with the exception of those 4 electrons, and it is converted to 4OH minus aqueous. So the overall reaction is H2 plus O2 gives H2O. This above reaction is the same as the hydrogen combustion reaction. However, they do not react directly. That is, the oxidation and reduction reaction takes place separately at the anode and cathode respectively, like H2O2 fuel cell. Other fuel cells are like propane and oxygen, methane and oxygen have been also been developed. Next is corrosion. That is one of the important one. We are familiar with the rusting of iron, and have you ever noticed a green film formed in the copper and brass vessels? In both the metals, it is oxidized by oxygen in the presence of moisture. This redox process, which causes the deterioration of metal, is called corrosion. As the corrosion of the iron causes damages to our buildings, bridges, etc. It is important to know the chemistry of rusting and how to prevent it. Rusting of iron is an electrochemical process. Now we are going to see the electrochemical mechanism of corrosion. The formation of rust requires both oxygen and water. That is, the iron is converted into iron oxide, that is rust. For that, it needs both oxygen as well as water, that is moisture. Since it is an electrochemical redox process, it requires an anode and cathode in different places on the surface of iron. The iron surface and a droplet of water on the surface. Here in this picture, it is shown, it forms a tiny galvanic cell. The region enclosed by water is exposed to low amount of oxygen, which acts as an anode. The remaining area has the high amount of oxygen and it acts as a cathode. So based on the oxygen content, an electrochemical cell is formed. Corrosion occurs at the anode. In the region enclosed by the water is here given. Okay, that is, at anode, oxidation takes place, that is iron dissolves in the anode region. Fe, that is converted to Fe2 plus with 4 liberation of 4 electrons. The EMF of this reaction is 0.44 volts. The electrons move through the iron metal from the anode to the cathode area where the oxygen dissolved in water is reduced to water. That is, at cathode, as usual, the reduction takes place. The reaction of the atmospheric carbon dioxide and water gives carbonic acid, which furnishes the H plus ions for reduction. Oxygen plus 4H and also plus 4 electrons gives H2O, that is water in the liquid state. The electrical circuit is completed by the migration of ions through the water droplet. So the overall redox reaction is 2Fe plus O2 plus 4H plus gives Fe2 plus 2H2O liquid. And the EMF is, for the oxidation, the EMF is 0.44 volt, and for the reduction, the EMF is 1.23. So if you are adding, you will get 0.44 plus 0.123, you will get 1.67. That is the EMF of the overall cell, or EMF of the overall reaction or the cell. The positive EMF value indicates that the reaction is spontaneous. Here the EMF value is positive, that is plus 1.67. If it is plus, we came to know this reaction is spontaneous. That is, it will take place without any stimulation. Fe2 plus ion are further oxidized to Fe3 plus, which on further reaction with the oxygen to form rust. The reaction is 4Fe2 plus water plus oxygen plus 4H plus gives Fe3 plus 4, Fe3 plus in aqueous plus 2H2O as liquid. That is 2Fe3 plus 4 water molecule gives Fe2O3 with 1 molecule of water, that is iron oxide monohydrate plus 6H plus aqueous. Other metals such as aluminum, copper and silver also undergo corrosion, but a slower rate than the iron. For example, let us consider the reduction of aluminum. Aluminum solid is converted to aluminum 3 plus with the liberation of 3 electrons. So aluminum 3 plus, which reacts with the oxygen in air to form a protective coating of aluminum oxide, that is Al2O3. This coating acts as a protective film for the inner surface, so further corrosion is prevented. Next is protection of metals from corrosion. How to protect these metals from the corrosion? This can be achieved by the following method. The first one is coating the metal surface by paint. Whichever is in the exposed to the moisture, we have to coat it by paint so that we can cut the moisture as well as the oxygen in contact with the iron. Next process is galvanizing by coating with another metal such as zinc. Zinc is a stronger reducing agent than iron, and hence it can be more easily corroded than iron. That is, instead of iron, the zinc is oxidized. So galvanizing is nothing but the iron metal is coated by zinc. Why? Because zinc is a stronger reducing agent. So instead of iron gets reduced, first the zinc get reduced and it protects the iron. Another one is cathodic protection. In this technique, unlike galvanizing, the entire surface of the metal to be protected need not be covered with a protecting metal. Instead of metals such as magnesium or zinc, which is corroded more easily than iron, can be used as a sacrificial anode, and the iron material acts as a cathode. So iron is protected, but magnesium and zinc is corroded. So this cathodic protection is nothing but the entire surface of the metal, whichever is going to be protected, that the entire surface need not cover with a protecting metal. Instead, metals like magnesium or zinc, which is corroded more easily than iron, can be used as a sacrificial anode. That means on the top we have the zinc or magnesium, so that they will corrode easily instead of iron. And our next one is passivation. The metal is treated with a strong oxidizing agent such as concentrated nitric acid. As a result, a protective oxide layer is formed on the surface of metals. This is the another one method. That is, the metal is treated with a strong oxidizing agent. If it is treated with a strong oxidizing agent like nitric acid, again the same thing, one protective oxide layer is coated on its surface so that the further corrosion is restricted. Next is alloy formation. Alloy, it is the combination of two or more metals and non-metals. The oxidizing tendency of iron can be reduced by forming its alloy with another more anodic metal. So the oxygen is combined with another metal which is having the more anodic metals. For example, stainless steel, that is an alloy of iron and chromium. So iron is added with the chromium, means we can restrict the corrosion or we can prevent the corrosion. Next is electrochemical series. We have already learnt that the standard single electrode potential are measured using a standard hydrogen electrode. So as a hydrogen electrode only you are taking as a standard measuring. The standard electrode potential at 298 Kelvin for various metal and metal ion electrodes are arranged in the increasing order of their standard reduction potential values, that is given in the tabular column. This series is called as electrochemical series. The standard reduction potential, that is E0, is a measure of oxidizing tendency of the species. The greater the E0 value, greater is the tendency to shown by the species to accept the electron and undergo reduction. That means whichever is having the more the potential, that will be gets oxidized. So higher the E0 value, lesser is the tendency to undergo corrosion. So what do you mean by that? If we have the standard potential value, the EMF value is more, then it have the less possibility of corrosion. And in this tabular column, we have studied the half reaction and the standard potential are given. On the top we have the plus, and at the bottom we have the EMF of -1. So the stronger they are behaves as a stronger reducing agent from top to bottom. And while we are coming here, the ions, those are all they have the reaction with the 2 electrons and the 4 electrons gives, and those are all acts as a strong oxidizing agent. The strong oxidizing part increases from lithium to fluorine, and here the potential is given, that is those are behaves as a stronger reducing agent. Okay, with that we finish this lesson, and followed by this I finish this lesson. Followed by this, I am giving you the question and answer in the form of a PDF, so you can read it and you can take it in your notebook, and whenever they are saying the notebook submission, during that time you have to submit the notebook. Is it clear to you? Okay, ma, thank you.